Welcome to the module. So, till now we have seen different circuits, different signal conditioning circuits for the sensors, as well as we have also seen the use of operational amplifiers as a signal conditioning circuits when we have a particular requirement or when we have to design a signal conditioning circuit for our sensor. So, in this module I will be explaining you, or I will be showing an experiment on signal conditioning circuit for acquiring an ECG signal, as well as to do a feature extraction, or that means a processing of ECG signal as a live experiment by using an operational amplifier. So, what exactly we do is that, so we will use ECG electrodes as a patch electrodes as well as ECG cables. So, where it gives us ECG signals which can be collected from our body, and that will be interfaced to our analog circuitry board. So, basically which contains which designed a signal conditioning circuit using operational amplifiers. So, as professor discussed in the class, why do we require signal conditioning circuit at this for this ECG acquisition, as well as the importance of a filters and the importance of an ECG signal. We will briefly look into how exactly the ECG signal looks like and why do we require signal conditioning circuits too, and we will discuss about the designing of signal conditioning circuit for extraction and for filtering out of filtering of an ECG signal to get a very clear ECG signal. And we also do some signal processing, meaning to extract features from ECG, may not be complete ECG features, we will be extracting a QRS peak peak, so that we can identify how many number of BPM, how many number of pulses that we are getting to calculate the beats per minute. So, in order to do, so either you can go with a digital way of processing it, or analog way of processing. So, since our module is completely on analog way, we will see how can we make use of an operational amplifiers as well as other analog circuitry in order to acquire, to process the signal and to do the feature extraction like finding out the ppm using op amps. So, we will divide this complete experiment into different subsystems. In each subsystem we will understand our requirements in this particular subsystem, and we will design that subsystem, we will do simulation. After doing the simulation, we will do the experiment on that particular subsystem. Once that is working as per our expectations, after doing all other subsystems that is required in order to do this processing as well as conditioning, we will interface each and everything and we will see whether we are getting an ECG signal or not. So, when we so in our case we will be we are going to design and build an op amp based ECG signal acquisition, conditioning and processing of PQRS wave and compute BPM. So, the whole idea is that we will be acquiring ECG signal and we will extract QRS out of it, and we will calculate how many number of peaks, QRS peaks we are getting in minute. So, that which can gives us BPM. As professor explained in the theory session, the importance of ECG signal, that as if you remember, it looks like something like this: P, Q, R, S, T, U and this one. So, this is P, Q, R, S, T and U, right. So, as we have seen in the in professor's lecture, that the importance of each and every wave, the amplitude as well as the time duration is very much important in order to understand the functionality of our heart. How we are getting the ECG signal? As we know that because of polarization and depolarization of our signals that we are receiving from the heart, that impulses are generally acquired by using some patch electrodes, so that we can visualize a signal something like this. So, in that signal, if I see, the pattern will be something like PQRS. So, each will have a proper defined timing as well as an amplitude. Any deviation from the standard values, that means the amplitude of P as well as the time duration of the P wave and the amplitude of QRS wave as well as the time duration of the QRS, T, peak and generally U cannot be easily visualized. So, any deviation from the standard values indicates that there is some problem in our heart, the working of an heart, right. So, in order to understand, one thing is that we should know how do we acquire an ECG signal, and moreover, in fact, if you see the amplitude of an ECG signal, it will be either in microvolts or in millivolts, and moreover the signal whatever we get is not a simple simple output voltage. We have to always take a difference between two sources. So, that means we require to do a differentiation, that is one thing, and moreover, since the signal to noise ratio is really poor in case of acquisition of ECG signal, that to a raw ECG signal, we require to have a proper signal conditioning circuit which can improve the signal to noise ratio, and we also require to have an filtering circuit to remove the unwanted signals which are available in the ECG signal. So, if I want to remove such systems, we should understand what are all the unwanted signals, why these are unwanted signals are coming into the ECG signal. So, in order to extract and process of any ECG signal, right. So, we have to interface our electrodes to our body. So, when you interface our body and when we are using an electronic circuit system, so there are different sources of errors that are introduced into the system. As professor discussed in the class, one major thing is power line interference, isn't it. So, what is nothing but power line interference? The power line interference is majorly due to the operating frequency of our equipments. So, generally in India the operating frequency is somewhere around 50 hertz. So, when we see the raw ECG signal and we compute in a frequency domain, we can see there is a peak, there will be a peak at every odd multiples of the frequency of our power line. So, that is nothing but at 50, 150 as well as 300 hertz. So, that signal is not required. So, that means 50 and 150 as well as 300 frequencies, more than those frequencies, we may not require all these frequencies, right. So, one way to remove that is, in order to remove that particular frequency, we should know what is our frequency of our ECG signal. Generally speaking, the ECG signal frequency will be somewhere around 0.05 hertz to 120 hertz, or generally they will also say till 100 hertz. So, this is the major operating frequency of our ECG signal generally. So, when I compare that frequency with the power line interference, so one portion, that means the frequency below 50 and frequency between 51 hertz to 100 hertz, that signal is required for us, right. And but frequency greater than 100 hertz, I do not require anything. So, if I want to remove the frequencies which are greater than odd multiples of our power line interference, that means 150, 300 hertz, I can just simply pass through a low pass filter, so that the frequencies greater than 100 hertz cannot be passed, so that other than 50 hertz power line interference, the other odd multiples of the power line interference can be completely filtered out. But in case if I want to filter 50 hertz signal, so if I remember, we can use some kind of a notch filter. So, how a notch filter looks like? So, something like this and like this. This is nothing but the frequency which we do not want to allow, and these are the frequencies which will be passed through. So, 0 to somewhere around 49 or 48 hertz we will allow, and from 50 and again from 51 or 52 hertz till 100 hertz till everything, till complete, right, we will allow. And since we also have a low pass filter, after the 100 hertz no signal will be sent, no signal will be received. No signal in the sense, most of the signals greater than the higher cutoff frequency of our low pass filter, the cutoff frequency of a low pass filter will be attenuated. So, as a result we cannot see the signal after 100 hertz. So, such a way one problem due to the power line interference can be eliminated. What else? What are all other signals that will interfere with our required signal? Required signal in this case is ECG signal. So, another one is nothing but our motion artifacts. Right. So, in order to remove these motion artifacts, right. Generally speaking, these motion artifacts will be somewhere around lesser than 0.05 hertz. So, it will be somewhere around 0 to maximum of 1 hertz, right. So, if I can have an high pass filter, if I use an high pass filter with a cutoff frequency of somewhere around 0.5 hertz, right, any frequencies lower than 0.5 hertz which are due to the motion artifacts can be completely filtered out. So, that we can have a signal from 0.5 hertz to 100 hertz, but our major intention here is to find out the BPM. So, if I know what frequency range that QRS peak, so BPM meaning beats per minute is generally being calculated by counting how many number of QRS peaks we are getting with respect to particular interval of time. So, right, in minutes, if I calculate in terms of minutes, I will get how many number of peaks we are receiving in a minute, uses the BPM, our heartbeat rate. So, in order to understand, if I know what is a general frequency of our QRS, it will be somewhere around a maximum of 20 hertz. So, somewhere around 8 to 20 hertz is the maximum frequency of our QRS peak. So, as long as since this particular frequency is required to us, as long as we can allow this particular band of frequency, and if we remove other bands of frequency like without unknowingly or unwantedly, we can compute the BPM, but we will try to figure out to use proper filtering circuits in order to not to even compute the frequencies even below 0.5 above 0.5 hertz and even below 100 hertz too, so that we can see the proper ECG signal in our oscilloscope DSO2. So, but if I want to design such a filter in order to have a proper filtering at proper cutoff frequency, we require to have a higher roll off factor. So, if you want to get a higher roll off factor, single one order filters are cannot be used, either we have to go with a second order or third order filters, and we already seen that higher the order the filters, more number of op amps and more number of components, more the complex the system, more and the cost will also be higher. So, since it is very not so feasible to do in our laboratory basis, what we do is that either we go restrict to either first order to or second order filter, right. So that the roll off factor when compared to first order, second order filters will have even higher. So, it will not allow, it will always have a proper cutoff. We will also have a look into that too, right. Now, how do we acquire an ECG signal? So, when we look into the figure 2, first thing we will see how exactly we do our complete processing by representation of a block diagram way. So, first thing is to the patient's body, what we do is that we will connect ECG electrodes and by using a connecting wires, ECG wires, and connecting it to instrumentational amplifier. Since the signal whatever we receive when you look into the figure 2, whatever we receive, so the electrodes are placed in such a way that one will be on our right arm, other will be on our left arm, and right leg will be acted as a ground. So, the signals whatever we receive, one will be RA versus ground, other one will be LA versus ground. So, the difference between these two signals are nothing but our ECG signals, right, the difference between RA and ground and LA and ground. So, two voltage sources basically in this case. So, I have to use proper amplifier or proper differential circuit in order to in order to do the difference between these two input sources. And moreover, when we observe the amplitude of ECG signal, the maximum amplitude within a range of 1 millivolt, right, and those are all really lesser amplitude, and moreover it will always have very high signal to noise very low signal to noise ratios, right. So, if I want to use it, and moreover the signals whatever we observe from RA to RL and LA to RL will look similar, meaning those two are always common mode signals, almost common mode signals. In such a case, and if I want to make a difference between these two independent signals, we have to go with an instrumentational amplifier. The reason why we go with an instrumentational amplifier, because instrumentational amplifier has its own advantage like very high input impedance, very low output impedance, and you can also achieve very high CMRR, which is nothing but common mode rejection ratio. So because of these common mode signals, because of instrumentational amplifier is having a very high common mode rejection ratio, even though the input signals are almost same, right, this can easily differentiate between the input signal that is being applied as an input to the system, and we can observe an output. And moreover, the other advantage is that the instrumentational amplifiers can be used to provide higher gains to the system. Since the amplitude of the EC signals are very smaller, we require to have a proper amplification stage too. So instrumentational amplifier can be used for all the purposes, so that the required gain can be set by using our instrumentational amplifier too. So in ECG amplifier stage, we will be using an instrumentational amplifier because of their advantages. Of course, differential amplifier, if we take it, even though instrumentational amplifier uses a differential amplifier inside instrumentational amplifier, we cannot go with a differential amplifier because differential amplifier has very low CMRR, and moreover the input impedance of instrumentational amplifier is very higher. The reason is that the input is directly connected to the non-inverting terminal of an op amp, because instrumentational amplifier is made up of 3 op amp based circuit. But whereas a differential amplifier, since the input has to be directly connected to the resistor value decides the complete impedance of the system. As a result, the input impedance of the differential amplifier is really poor. So we cannot go with an differential amplifier. So that's why we are going with an instrumentation amplifier, because of these advantages. Then the whole idea is that we have to find out BPM. That we should never forget. So what do you mean by BPM? Which can find out, if I can find out how many number of peaks that we are getting, QRS amplitudes per minute, that is nothing but our BPM. Now what are all the errors that we have seen in the class? So few things we also discuss even in the session. One is power line interference, other one is motion artifacts, right. So how do we eliminate it? So as we have already seen the sources of an errors, we have also discussed what kind of filters to be used to. So one major filter we require to use is low pass filter with a cutoff frequency of 100 hertz, and high pass filter with a cutoff frequency of 0.5 hertz, then notch filter with 50 hertz frequency. So these are the major filters. So in this particular block, in this particular subsystem, we will be designing a filtering circuits which can remove all the artifacts that is required to process our ECG signal. Then why do we need a half wave rectifier in this case? The reason is that we require to know how many number of QRS peaks, but when we look into our peak QRS wave, we can see that there is one peak here. Now there is one more peak, this is called valley, negative peak, right. Another one is R is also another peak, then S is a valley, right, maybe a negative peak, and T is also peak and U is also peak. But our interest is only to look into positive peaks, but I do not want to allow negative peaks to pass through that. So how can you do that? If I use an half wave rectifier can only allow the positive signal, and it will suppress the negative signal. As a result, I can only see a positive peaks here, right, something like this, right. So this is nothing but our QRS. Wait, again we will draw. So P R T U, right. So I can easily eliminate our negative peaks. Now so our whole idea is to find out BPM, again remember that. Now from the signal, how do we calculate the only peak of R? So if I want to calculate only peak of R, I have to understand how do I differentiate between a peak and a point, right. When I do the digitization of the signal, we can take a different samples at different intervals, right. But how do you decide this particular value is a peak? So, in order to do that, I have to compare the peak value with the next subsequent value as well as the preceding value. So, that means for example, like say I take this particular value, let us say this is some x, and if I compare with x1 as well as x2, if x is greater than x1 as well as x is greater than x2, that means the present value, if it is greater than from the previous value as well as the next preceding value, then I can say the x is nothing but a peak. If I do that an algorithm, I can easily find out how many number of peaks that I have in the ECG signal. So, in this case we have P one peak, R one peak, T one more peak and U one more peak, but I may not require all the peaks, I require only R peak. But how do I differentiate which is a P peak, which is R peak, which is T peak and which is U peak? It is very hard to differentiate, but if I can pass only the peak of R and by neglecting other peaks, right, I can only get R peak, and if I count how many number of such R amplitudes are getting, R peaks are getting with respect to 1 minute, I can easily calculate BPM. So, that means I have to know some knowledge on QRS peak too, I have to know some knowledge on ECG signal too. So, if we recall our what professor said in the class, we understood that the QRS amplitude peak is comparatively very large when compared to the other peaks in the ECG signal. So, when I say comparatively very large, if I take some threshold, if I put some threshold, that means out of complete ECG signal, what is the maximum peak that I am getting? In that maximum peak, I will fix some threshold somewhere around 70%, somewhere around 50% of the peak. So, like say some this threshold, so that it will allow only the R peaks to pass through, and whichever the peaks below the threshold it will not allow. Then I can easily find out the R peaks, and how many number of R peaks if I can calculate, my job is done, right. So, in order to do that functionality using operational amplifier, I have to design a circuit. Designing that circuit is nothing but peak detector circuit and thresholding circuit. Then after doing peak detection and thresholding, I have to compare. So, whenever I get a peak, I have to count it. Since the counter is a digital part, what we are planning to do is that either we will show it in a CRO whether we are getting the peaks or not, or we can use some kind of a triggering input where if it can generate some high voltage whenever there is a signal, our job is done. And if I connect that to some kind of a counter which can count only when I get a high peaks, then it gives us a complete indication of beats per minute. So, in 1 minute how many number of peaks that we are getting, that indicates our BPM. So, if I can do all these processes, all these conditioning circuits and processing circuits using operational amplifiers, it will be very great. Now, we will see how can we implement, how can we design all such things and how to extract ECG signal from our human body, right, and how do we visualize the signal in our CRO, everything will show you in this case study experiment. So, but before giving you the live experiment on ECG signal, we have to build the circuits, we have to split the complete experiment into different subsystems, and we have to design those subsystems as we have seen in the block diagram, and we have to simulate that, and experimentally we have to verify whether the circuit is working as per our expectations or not. Then after interfacing everything, we will connect it to the patient and we will see whether we are getting ECG signal or not. That is the whole idea of our experiment today. So, we will go one by one. So, as I already discussed with you, how do I do the ECG amplification? So, we will take an instrumentation amplifier. So, in this case I am taking INA 128, INA 128 is also an instrumentation amplifier. So, how we are taking is the positive terminal will be connected to the one voltage source and the negative terminal is connected to the another voltage source, right. One terminal is connected to the positive terminal of instrumentation amplifier, another terminal is connected to the other terminal of an instrumentation amplifier. So, the difference between these two signals gives me the output voltage, right, but we have also seen that the amplitude of the ECG signals are really poor. That means I also have to set some kind of a gain. So, when we look into the data sheet gives us what resistance, what RG resistance if I use, it is equivalent to particular gain. So, in this case we can use a pot, with a value of 100 or 200 ohms. So, if we feel that that particular resistance is good enough, that amplitude, that gain is good enough, we can remove it. So, in this case we will be keep on tuning it, and whenever we feel that we are getting a very good amplification factor, we will stop it. Generally speaking, we will be using a gain of 500 sorry. So, we will be using a gain of 500 to 1000. Now, what is the use of this resistor and capacitor? So, this acts as a low pass filter. Any noises that are getting from the input signal will be completely removed off. So, this circuit is a completely instrumentational or the amplification stage of an AC signal. So, in this experiment what we will show is that this particular block we will take it to the last thing. Before, once we finish all the filtering circuits, once we finish other parts of our logic, we will come back to the instrumentational amplifier, we will check the difference between the instrumentational amplifier and the differential amplifier, then we will interface to that. Then we will go to the next one, which are nothing but our pre-processing. So, we have already seen, right, one is power line interference. So, in order to remove our power line interference, we have to do notch filtering of 50 hertz and low pass filtering. So, that low pass filtering value of 100 hertz. So, the odd multiples of 50 hertz can be completely removed. Other one is a contact noise. This contact noise, as well as the baseline wandering, as well as EMG noise and patient's electrode motion artifacts. So, can be completely removed by passing through an high pass filter. So, what do you mean by baseline wandering? When we see an ECG signal we should get in one base, but instead of getting in this way, we will be getting by changing in the offset, something like this. So, it will be with respect to the ground, it will be always fluctuating, that is called wandering, baseline wandering. So, in order to remove that, the frequency, if I know, the baseline wandering frequency will be somewhere around 0.5 hertz. So, by passing through an high pass filter, even that can be eliminated, and motion artifacts we have already seen, right. So, if I can design a notch filter, high pass filter, low pass filter, the noises due to these particular contaminants, ECG contaminants, can be completely filtered out. Now, that means in this pre-processing stage, one is we have to design a low pass filter, and the cutoff frequency is nothing but 100 hertz, and we have to design a high pass filter, and the cutoff frequency is 0.5 or 1 hertz, because our wanted signal is QRS. QRS is somewhere around maximum of 20 hertz. Then notch filter with a center frequency of 50 hertz. So, these are the major 3 important processing filtering blocks that we are going to use in our experiment today.